Hello, this is Mr. Stansbury. I'm going to take you through the notes on graph simple rational functions. At the end of this, you should be able to say, I can apply transformations to graph rational functions, and I can describe the transformations of a rational function. Okay, so let's get straight into it. Use a table to sketch a graph of f of x equals 1 over x. So if you haven't seen this before, you probably have really no idea what's going on here, what this graph's going to look like. So what we can always do is just make a little table. Okay, so if we just go from -2 to +2, that should give us a pretty decent idea of what this is going to look like. Okay, so if we plug in -2, that's 1 over -2, which is -1/2. 1 over -1 is -1. 1 over -1/2 is -2. 1 over 0, can't divide by 0, that's undefined. 1 over 1/2, you flip the 1/2 over, and that turns into 2. 1 over 1 is 1, 1 over 2 is 1/2. So now we've got enough info to graph this here. So at -2, we're at -1/2. -1, we're at -1. -1/2, we are at -2. At 0, we're undefined, so that is what we call an asymptote, right? Which means that this graph will get close to this line here, but never actually cross this line. Okay? Now we can get, let's see, at 1/2, we're at 2. At 1, we are at 1. And at 2, we are at 1/2. Okay, so these graphs are going to go like that and like that. So we figured out this vertical asymptote right here because it's undefined, which means it can never cross. And then what is something we can never divide by? We got to set this denominator here equal to 0. So x can never ever equal 0 because you can never divide by 0. So then that means that there's a horizontal asymptote here at 0. Okay, so we got these dotted lines here, and then this graph is going to roughly just kind of come through, look something like that on this side, and then on this side it's going to come through, look something kind of like this. And it's going to get closer and closer to each of these asymptotes, but never actually hit them. Okay? So, identify domain and range. So, domain is all the real numbers except for 0, right? So we can just do r not equal to 0. And then the range is what the y's can be, and that can be everything infinitely high or low, but just can't equal 0. So same idea. Real numbers that are not equal to 0. Describe the end behavior. So as x is approaching -infinity, what is f of x or y going towards? So as we're going closer and closer here, farther and farther out here, we're getting closer and closer to 0. As x is going to 0, and then it's got this, looks like it's a power of negative, which I know looks weird. That basically means as you're approaching 0 from the negative side of 0. So here's 0, and then the negative side, this is going to be the negative side over here, and this is going to be the positive side over here. So here's 0. If you go over here, approach from the negative side of 0, what's happening to this graph? It's getting closer and closer to -infinity. And then as we approach 0 from the positive side, so we go over here and find the graph and work back towards 0 from the positive side, this is going towards positive infinity. Okay, and as x is approaching infinity, as x is getting bigger and bigger, this graph is getting closer and closer to 0. Okay, identify the asymptotes. We did that already with our little graph here, right? So we have this one here. Whatever axis it crosses through, that's how we define it. So this crosses through the x-axis, so we've got x equals 0. This crosses through the y-axis, so that's going to also be y equals 0. Those are our two asymptotes. Identify the intervals of increasing and decreasing. So increasing, always as we're reading left to right, and decreasing as we're reading left to right. So decreasing, 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 And then up here, it's still decreasing. So there is no intervals of increasing, but decreasing. We go from negative infinity to up to 0. Let's do this and then put the x in the middle and then 0. So when x is greater than negative infinity all the way up until it gets to 0, it's decreasing. And then also after, from when we start at 0 and we get x is greater than 0, less than positive infinity, then it's also decreasing. Okay? Okay, we're going to look more into some of the graphs here, but first let's take a quick little comedy break.
Half hour, the captain finally gets on.
Oh, folks, let me tell you what's going on up here.
I hope it's good. Has that ever followed anything even remotely good?
Let me tell you what's going on up here. We found a big bag of money on board. And the tower has instructed us to divvy it amongst all you passengers. We apologize for the delay. The problem is each individual stack is getting so high they keep toppling over. And the rubber bands we've been using keep snapping on the sides of these bundles. Apologies from the flight. Wow.
All right. Let's take a look at this. So we're going to sketch a graph of this here. So a little different than the first one here because we've got some extra numbers going on in here. But here's the basics of this here. This +1 here, that there is going to be our horizontal asymptote. Okay, so at +1, we're going to have an asymptote right here. Right, so we've got horizontal asymptote, it crosses through the y-axis, so we get y equals 1. Okay, now if you remember from before, we can never divide by 0. So then our vertical asymptote is going to set this denominator here equal to 0. So 2x minus 4. Set that equal to 0. Add 4 to both sides. 2x equals 4. Divide by 2. X equals 2. So now we have a vertical asymptote at x equals 2 right here. Oop, started going sideways there. Right? So the graph is going to approach these lines, but never actually reach those lines. So now, when you want to know what it's going to look like, honestly, I feel it's probably pretty easy to just plug in a number on one side or the other of this vertical asymptote here, right? And since it's positive, we know it's going to be, the positive is going to be here and here. If it's negative, it would be here and here. But we can just kind of plug in a couple of points and away we go. Let's plug in 1 and see what happens. So 6 over 2 times 1, minus 4, plus 1. So that's 6 over 2 minus 4, 6 over negative 2. So it's negative 3 plus 1 is negative 2. So at 1, we are at negative 2 here. And then let's see what would happen if we plugged in 0. 6 over 2 times 0 minus 4 plus 1. So that's 6 over negative 4. So that's what? Negative 1.5. Excuse me. Negative 1.5 plus 1. So it's negative 1/2. So at 0, we're at negative 1/2. So we can tell the graph's going to look something. Oops. I'm not very good at drawing these lines here. Something kind of like that-ish. This, of course, would be a little bit more straight. You get the idea. Okay, and then it should mirror image what we got over here. So if we plug in 3, so this one is 1 off, and we had to go from this line here. We went down 1, 2, 3. If we plug in 3 from this line, we should be going up 1, 2, 3 right here. Let's double check it to see that it works. So 6 over 2 times 3 minus 4 plus 1. So that's 6 over 6 minus 4. 6 minus 4 is 2. So 6 over 2 plus 1, that's 3 plus 1, which is 4. And look, there it is, right there at 4. So this one here, we went over 2 that way. So we're going to actually go over 2 this way and down 1.5. So we go over 2 this way and up 1.5. So this graph on this part here is going to look something kind of like this. Okay? Okay, last example here, example 4. Write an equation of the graph shown in the form g of x equals a times 1 over x minus h plus k. This is also the same as if you multiply this a through, it's basically just a times 1, so that's going to equal a over x minus h plus k. Okay, that's the formula you'll more likely see things in. So, if you'll remember here, let's see, this horizontal asymptote is always going to be what our k is, if you'll remember from the page before, the example we just did. So, negative 3 is going to be what our k is, right? That's our horizontal asymptote. Vertical asymptote is what's going to make the denominator equal to 0, right? Because that's what x can never be. X can never be 1, so that means x minus 1 is going to have to be our, let's see, we'll write it like that. X minus 1, because x can never equal positive 1, right? Another way to look at that is to say, oh, when x equals 1, it can never equal, x can never equal 1. So if we want to solve this so that we can figure out what the denominator is here, we subtract 1 from both sides and we get x minus 1 equals 0. We know the denominator can never equal 0, so that's why this x minus 1 goes right there. Okay? And then the last step, g of x equals, our last step is to figure out what this a is. And really the simplest way to do that is think of this as your new vertex. So if we plug in 1, right, ignoring these numbers on this x and y axis here. So if we plug in, if we go over 1, if a was 1, if we went over 1, we'd go up 1 and be right there. Okay, so then that means a would be 1. So of course it doesn't do that. If we plug in 1, we go down 2 from this point. So we go x is 1, y is negative 2. So that means our our a is negative 2. Okay, and that is our formula. And just to double check to make sure that this works, you can always plug in a couple of these points. So like if we plugged in 2, we better get negative 5 out, right? Equals negative 2 over 2 minus 1 minus 3. So g of 2. Negative 2 over, that's 1. That's negative 2 minus 3. Guess what we get? Negative 5, which is that one right there. Okay, you can also do the same with 0. Okay, that's all we have for graph simple rational functions. If you have any further questions, please feel free to ask in class. Thanks.